Starting from where we stopped the last time we met, we dealt with explicit modeling, and then we dealt with parametric modeling. What we're trying to do here is to make you to be familiar with the terminologies that you will encounter in the course of this course and in the course of you being an architect that is vast in navigating in the digital space for his profession. So today we're going to go a step further by looking at associative modeling. So in this lesson, like you are seeing here now, you will build upon the knowledge of parametric modeling by developing a complex associative design system in the form of a waterfront tower. The following exercises address a tertiary phase of the design process, in which a developed layering of associations creates a robust and cohesive parametric design. This layering of associations allows for the iterative exploration of multiple design solutions that meet the design criteria. So looking at what we have here now, in terms of being able to construct an associative building mass, we'll go ahead and try to use our software tools to create an associative building mass. Like I explained earlier, this course, you can use AutoCAD, you can use SketchUp, at the same time, you can use Revit. But for emphasis and at this 200 level, it will be very, very easy for you to master how to use SketchUp to carry out your task in this environment. So I'm expecting that by now, everybody in this class, you've installed SketchUp on your systems, and you have been going through the learning resources to understand how to use it and how to manipulate it. So let me open a CAD view. Let me open an AutoCAD view where we will try and perform some exercises. Okay, maybe let me look for a typical 3D file. That we've used before. I hope it's still close by. Okay, we can proceed even without this. Okay. I think I've seen something. Okay. Okay. We can use this for what we want to do. Okay. So we will attempt to draw exactly what we are seeing here. We'll attempt to use the tools available to us. Like I said, we can do this in SketchUp, we can do this in Revit, we can also do it in AutoCAD. But for the purpose of this class today, we're going to use AutoCAD to be able to do something like this. Please bear in mind that immediately you're logged out, we are going to log back in to continue with what we are doing. Please bear that in mind. So first of all, to create the shapes that we want to create here now, we'll use different commands to be able to do that. We can decide now to select polyline. And I want you to look at our UCS. I want you to look at our UCS. This UCS is one of the most important things that you need to learn. You need to understand how to manipulate so that you can be able to create your work with ease. With ease. If you look at the way our UCS is placed, it means that whatever we want to model now, we will be modeled along the z-axis, here, this one here. Look at the UCS here, the coordinate system. You can see that your y is pointing forwards, your x is pointing in this direction, and then your z is pointing towards us. But that's not what we want to do now. So we go to tools, we go to new UCS, we select world. So it places it like this. The y-axis is pointing this way, x-axis is pointing this way, the z-axis is now pointing upwards, which means we can use this now to model whatever I want to model. For example, we can start to go to our polyline. Select your polyline. You can draw things like this, just a straight line, another straight line, like this, and then I'll bring it here. Instead of just clicking there, I will type C because I want it to be closed. So it's now a closed polyline. At the same time, I can select the rectangle command, and I'll draw something like this. Okay. At the same time, I can go ahead and select okay, let me select the box. I can select box. Okay, look at what we just did here now. We just drew this. We've not added any 3D properties to it. It's just a closed polyline that we can use for a 3D. So we just click here on this one. It looks like they look like they are the same thing, but it's not the same thing. Once I click now, I've determined X and Y. The system will give me an opportunity to determine what Z will become. So once I click now, you can see that it did not relinquish my position on that object. So I will move up now for you to see what I mean. I'll move up now for you to see what I mean. So, okay, maybe I will just stop it here. And I'll now show us how we can transform this object to whatever we want it to be. For example, I will select this command called press and pull. Press and pull. I will place my cursor on top of this place. And once I do that, it's highlighted. So I will press and I'll pull it up. You can see that I've succeeded in transforming that object. Okay. Sorry, the system is taking time, maybe because the file is heavy. You can see that because this is also a closed polyline, this press and pull command works here. Once I place my cursor inside this place, I can click and also drag it to whatever height I want it to be. I can also come to this edge now of this object. Wow, the system is taking time to respond to these commands. So these things we're doing here now will give you an idea of the kind of systems that you're supposed to have. So we need a system to do your work in such a way that you will not be frustrated. Okay, I can do the same thing here. Press my mouse and pull. Can click here. Okay. Let's try to create some transformations on this object that we created here now. Okay, let me separate the two of them. You can see the base object is still there, while this one has moved. Okay. So I'll still use this press and pull command again to give this one a measure of height because of what I want to do with it. Sorry for the time it takes for the system to analyze information and respond to my command. Okay, let's maybe what we're going to do here now, since this thing is taking a little bit of our time, we'll still continue with it. But first of all, let's run through the lectures, then we can come back and now start doing the practical aspect of it little by little. Please, once we are logged out, I will log out. Okay. In fact, I think what I should do now is to. Okay, you are all welcome back. I think we can continue now. We've been dealing with constructing an associative building mass, being able to create a mass and apply some transformations on it. That's exactly what we're trying to do here. Now, like we're saying that the building mass is extruded from the outline of the site. It's extruded from the outline of the site. What it simply means that you have a site, you have your building footprint, the external walls of your building, that block that defines your building. Now, if you are using CAD for that particular work, you can create that building footprint as a closed polyline, and then you can extrude it and apply different kinds of transformations on it. And then adjustment to the positioning of the vertices, the edges, and faces are made to add additional details. Let me just show you exactly. Okay, let me go back to this. Look at this particular image that is here. This line you're seeing in purple. These are vertices. All these small dots you are seeing here, these are what we dealt with in the first class, dealing with knobs, points, vertices, edges. So these vertices, these edges, these knobs, these are the points that you can click on and apply transformations on this particular object. If you remember what we did and during our CIT class, that we use grip to grip an element, and then on that blue box on that grip, you can right click on it and apply different operations on that particular object that you created. It's a little bit similar to what we are doing here now. Here we're working in 3 dimensions. So each of these vertices, I can click on this and drag it, and at the end of the day, this shape you are seeing here now can look like the face of a human being. You can even use this to model a human being. You can create the head from here, can create the other body parts. Transform it by transforming all the vertices, the edges, the knobs, and the surfaces. And now we can manipulate the sub-object levels of the mass until it arrives at a stage in which we are satisfied, which means you can start with a box. And then from that box, you can create a car. You can start from a box. Then from that box, you can create a human being or a human head. You can start from a box. And that box, from it, you can model a building. You can model a building. So you need to understand that these are opportunities. Those edges, those vertices, they are called the sub-object levels. And you can select those sub-object levels and apply different kinds of transformations on them. With these vertices, edges, corners, we can apply parametric control on this object, and it will respond the way we want it to respond. Let's just treat the theory aspect of it. We'll have opportunity to go in details. Now, in order to add parametric control, and also in order to explore variations more precisely, we need to begin by adding dimensional parameters, which means enabling increased degrees of control through numeric input. And now the first dimensional parameter that you apply to the building mass is a height constraint. By the time you start using Revit, you start understanding what constraint means now. You know, we can define a parametric formula associating the height control to other dimensions such as width. I want you to understand something, and that is why it's very, very important that these things are dealt with at this time in your career. That you understand what these parametric formulas are. We need to understand that there's a measure of scripting that goes into parametric objects. It's just creating associations between one object and the other. And that when a transformation is performed on one, it automatically affects the other. If you have a parametric object on a model, that's a wall now, and you have other objects with associated parameters. For example, if you bring a door to where a wall is, automatically that wall opens up to accommodate that door. Now, when you delete that door from that position on your model, the wall flows back. So this is the meaning of objects that have parametric properties, objects that have a measure of intelligence, which means once you perform certain operations, the other ones are transformed accordingly based on the parametric formula that is associating those elements. We also need to learn how to explore design alternatives. In design computing, it is easy for you to explore design alternatives. Now, when you're using the initial parametric mass that you created as an underlay, you can easily create additional design options, which you can easily explore in line with your design intent. Now, for the purpose of producing different kinds of design iterations, a series of profiles can be created using associative snapping, which constrains profiles to the base mass. I think what we need to do here is to create a tutorial on how to manipulate and explore all these options. We can create that and then share it on Moodle, and also create a link so they can have access to it and understand it very well. Because the time we have here might be asking for too much if we're expecting that we should be able to explore all the opportunities for parametric associative modeling and exploring design alternatives. I want us to talk a little bit on construction of an adaptive component mass. I don't want you to be confused with these terminologies that we're using for this. These are things that are very, very easy for you to manipulate if you understand the idea behind the principles that governs this operation. Now, in construction of an adaptive component mass, the adaptive component family, it utilizes several adaptive point types as the basis for constructing parametric reference geometry. Remember, we talked about point types. You know that a line, 2 points that are joined together. You know, including a curve. The curved line is also lines that are joined, maybe with a spline. Now, we're saying here that layering of parameters, this can be used to create complex systems relatively quickly. Now, some of these adaptive components, they can be nested in mass and pattern-based cutting system families, providing flexibility in system layering. I'm sure we all understand what layers means. It means to add parameters upon parameters on an object. Let me explain to you in the ones that you can easily understand. You have a layer, you have a wall. That wall has certain parameters, or you can call them properties that are associated with it. That line, it has a line width. It has a line tab. It has the line color. Several other parameters that are associated with it, that particular element. So that is the same principle that is adopted in constructing an adaptive component mass. You can look at what we have here now. That you can create a mass, and after creating a mass, you can easily add a floor to it. Look at this one, or just a mass that was just created. But here, if you look closely, you can see that floors has been added on this particular model. These floors here are defined by just lines. The walls also are defined by lines, by surfaces. So at the end of the day, these lines that define these floors can be added some associative properties, some parametric properties that at the end of the day, it will be a floor. And the associative parametric properties that is embedded inside of it can depend on what you want to create. It can be a wooden floor. It can be a concrete floor. It can be a composite floor of concrete and steel. It can be a completely steel floor, depending on what you want to create. But first of all, it begins by creating the footprint, extruding it, and then adding other associative properties like floors, and then giving more details to those properties again. Now, when you talk about component hosting, that you can guide curves to form the framework for the conceptual mass that you want to create. Usually, this is essentially a swept solid that has the advantage of being fully parametric. Now, shape handle points are hosted to guide curves. And then once in place, the profile can be quickly copied to produce a series of profiles, which can then be swept to form a solid mass. Yeah, we are looking at the opportunities of exploring design alternatives. We're looking at opportunities of exploring design alternatives. And then in exploring the design alternatives, we do that with controls in place. It's easy to compare the advantages and disadvantages of each approach. And now, when we talk about controls in place, what it simply means is that each of those objects that you want to transform in creating those design alternatives, once you select them, it has vertices, it has edges, it has points, and surfaces. So each of those each of these controls can be selected to transform that object to whatever you want to transform it to. Now I'm saying here that the floor mass schedule can be used to quickly determine the floor area determined by each geometric solution. And this can be, you can use panelization options for each alternative. And this can be explored using Autodesk Revit software's built-in tools. So I will go ahead and generate a video tutorial that describes how to perform these operations and I will post it on our platform so that you can have access to it for future references and in readiness for your exams.